Hi, I'm Ines. I'm the co-founder of Explosion and one of the co-developers of spaCy, an open-source library for industrial-strength natural language processing in Python. In this video, we'll be taking a deeper behind-the-scenes look at spaCy 3. This video really goes into the how and why, so if you're more interested in the what, check out our other video on this channel. In that video, Matt and I talk about all the new features like transformer-based pipelines, the training system, workflow management, and the new APIs. In October 2019, I was invited to Chennai to give a keynote at PyCon India. It was an amazing experience, we had a great time, and I met many cool people from the local community. The title of my talk was Let Them Write Code, and it was about building developer tools and why good developer tools need to be programmable, instead of trying to anticipate everything that the user might want to do and only offering leaky abstractions. In the talk, I also showed some practical ideas for how to make developer tools more programmable, without compromising on the developer experience. Many of those ideas were actually directly inspired by what we were working on for spaCy 3 and its machine learning library Think at the time. And now that the new versions of spaCy and Think are released, you can see those ideas in action. In this video, I'll show you some of the design patterns that made it into the library and explain what's going on under the hood, how we've implemented them, and most importantly, why. I'll also share some lessons we've learned about developer experience along the way. When spaCy was first released in 2015, the way people did NLP was quite different from the way people are doing NLP today. And I'm not just talking about embeddings, transformers, and transfer learning. It's not just a question of the same people doing the same types of projects but running newer algorithms. Today, far more teams have at least one person with quite a lot of experience in machine learning, and organizations have learned more about what types of projects are likely to get results. Deep learning, by its nature, also gets you involved at a different level of abstraction. Once you get into the details, you may want to add layers to a model or access the raw outputs. These are workflows that we want to support in spaCy. But at the same time, we want to stay true to the library's vision of providing useful pre-configured building blocks you can use right away. We want to maintain the library's ease of use. But to do that, we need to get the architecture right. We can't sweep the complexity under the rug. Machine learning is complex. If we want to provide a better developer experience, we need to face this complexity head-on, and not just cover it up with a bunch of abstractions and hide it away. spaCy 3 provides a powerful developer experience for customizing pretty much every part of the pipeline and neural network models, including the ability to plug in any custom models implemented in any framework. At the same time, we want to make it easy to get started and provide reasonable defaults so new users can get going, be productive, and train models as quickly as possible. And we want to make sure there's typically only one way to do things. Previously, training models on the command line was more convenient, but less extensible, and writing your own training scripts was more flexible, but also more complicated, especially when it comes to getting the little details and hyperparameters right. spaCy 3 focuses on one workflow for training models, using spaCy train on the command line, with a single configuration file defining all settings, hyperparameters, model implementations, pipeline settings, components, component models, and initialization. The config isn't only the single source of truth, it also includes all settings and records all defaults. Even if you're training with a default configuration and aren't planning on customizing anything, your config will still include all settings. Given the same config, you should always be able to reproduce the same results. The config will be passed as a dictionary and can include nested sections, indicated using the dot notation. For example, components.ner. Under the hood, it's basically a variation of Python's built-in config parser that's also used to parse things like the setup CFG. But we're taking the config syntax one step further and also allow any JSON serializable values that are parsed when the config is loaded, as well as a more flexible variable interpolation that lets you reference config values in nested sections, as well as whole sections. What makes the config special is that it doesn't only support JSON serializable values, but also references to functions that are used to create an object, like a model architecture, an optimizer, a corpus reader, and so on. You don't want to fall into the trap of programming via a config file and having the config define logic. Python is perfectly fine for that. So instead of defining the actual logic, the add syntax lets you refer to a function that creates an object. For example, add optimizers lets you define the string name of a function in the optimizers registry. All other settings in that block will be passed to the function as arguments. When the config is resolved, the functions are called to create the objects, like an optimizer. The config is resolved bottom up, so we always start at the outermost leaves and work up the tree. This means we're able to flexibly compose functions and pass the object returned by one function into another as an argument. Let's take the optimizer and learning rate as an example. There are different strategies for how to vary the learning rate, and it's often something you want to customize. A more classic approach for this would be to initialize our optimizer with a bunch of settings, including how to create the learning rate schedule. That works, but you'll be hitting a roadblock pretty quickly. There are lots of arguments, many of which only make sense in certain combinations, and it becomes difficult to swap in a fully custom strategy, like something new you just read about in a paper and want to try out. So the more composable solution is just pass in the learning rate schedule itself as a generator that yields out the sequence of learning rates you want. On the config level, this means the learn rate argument of the optimizer is a subsection that references a function. As the config is resolved bottom up, the learning rate function is called first, and its return value is then passed in when the optimizer is created. The same applies for pipeline components and model architectures. Previously, a pipeline component would create its neural network model, and it will be customizable with a few settings. We call this pattern top-down configuration, and once you're thinking about it, you'll probably see it all over the place, and you'll notice the problem it introduces. One is that the topmost object needs to receive settings and then pass them down to other objects it creates, and functions it calls, which then pass down settings to whatever they call and create, and so on. This means that one value may have to be passed down in multiple places. As soon as you miss passing it on, a default may get activated without you realizing. For instance, a pipeline component might have a setting to define the width of its embeddings table. It then creates a model instance and passes down the width. The model then creates one or more layers using that number. If you forget to pass it down to one layer, it might fall back to using its default width, which might be different. With a top-down configuration, you can very easily end up with mismatched configuration and very subtle and deeply nested bugs that are difficult to track down. To avoid this problem, you want to build your trees of objects bottom up. You don't want to pass in settings and have your function create an object with them. You want to pass in the instance instead. This stops the config from being passed along. In spaCy 3, trainable components are typically initialized with a model instance, which is defined in the config. Model architectures often also take sublayers created by functions. This means that the component doesn't have to be in charge of passing down a bunch of settings. It also allows components and model architectures to be modular. If you want to experiment with a different architecture or embedding strategy, just swap it out in your config. Now, you might be looking at this and ask yourself, why on earth are we doing all of this? We're writing functions that we're then assigning string names to so we can use those in a separate file. Why not just use the functions directly? Well, as much as a pipeline needs to be programmable, it also needs to be serializable. Serialization is the process of converting state, like a Python object or data structure, into a format that can be stored or transmitted and reconstructed later. For example, saving a model you've trained to a directory on disk and loading it back later. When you recreate your object, you obviously want it to be exactly what you saved. In the context of spaCy, this means that the pipeline should use the same language and tokenizer settings, the same components with the same settings, model architectures, and hyperparameters, and access to the same binary weights. So when you load back a trained entity recognizer, spaCy will create the component, configure it, and load in the data. You also want to limit what you save to what's necessary, and use a safe format like JSON wherever possible, not just pickle the entire object and make the user execute a bunch of arbitrary and potentially unsafe code. spaCy's built-in pipeline components implement their own serialization methods that take care of saving and loading the settings and weights. So given a directory and knowing that it's an entity recognizer, spaCy will be able to reconstruct the object. However, this gets trickier when the objects that need to be created are defined by the user. In spaCy 3, pretty much every part of the pipeline and training process is configurable with custom functions. You can plug in your own model implementation for a pipeline component, tweak the embedding layer of an existing component model, use a custom optimizer or batch size schedule, or swap out the function that streams in the training data. A lot of these customizable parts are used in different places across the core library, like the functions used to create custom pipeline components, or the settings that define how to initialize a blank pipeline. We don't want to keep passing those functions around all the time. Instead, we want spaCy to be able to ask, hey, is there a function for a component called relation extractor? And do we have a function to create a learning rate schedule called slanted triangular? Basically, we need a central place to store and register our functions, a function registry. Function registries let you map string names to functions. That's it. It's a simple concept, but very powerful. A string name uniquely identifies a function that creates an object, and given a string and a global registry, we can always recreate it. The underlying implementation, which we've open sourced as a lightweight mini library called Catalog, is pretty straightforward. We keep a global registry, like a dictionary mapping strings to functions, and use a decorator to add the function it decorates to the registry. It also supports registering functions via Python entry points, so third-party packages can expose functions for an existing registry without requiring the user to even import the package at all. Now, within the library, we can simply look up any string name in the registry. To register a custom function, all the user has to do is decorate it with a registry decorator and assign it a name. This allows users to easily customize behavior that's very deeply nested in the library or within other functions. And we're able to store this information in a safe format, like a JSON serializable config file. If the registered functions are available, meaning if the decorator runs, the library will always know how to create an object. This is very convenient, but it depends on a simple premise. We need to know and track how an object was or expects to be created. If all we have is an object, we're not able to create it again. This is, by the way, also the reason we ended up making one significant change to the Pipeline Component API and introduced a decorator to register custom components. NLP.addPipe is now only allowed to take a string name instead of the component function itself. As I've mentioned before, many of the new features in spaCy 3 are a result of rethinking the developer experience around inherently complex tasks. We want to provide workflows that are powerful, extensible, but also easy to use. And at the same time, we have to accept the reality, which is that bugs and mistakes happen. Nobody writes perfect code. There are two ways to deal with this. One is to catch mistakes before they happen and prevent them entirely. And the other is to catch mistakes more easily when they happen and help the user resolve them. In spaCy 3, we finally dropped Python 2, so we were able to embrace some of the newer Python features, like type hints. Type hints let you define the expected types of variables. For instance, adding colon in to a function parameter lets you declare that the value should be an integer. Static type checkers like MyPy can then analyze your code and point out potential mistakes, and modern editors can offer hints and autocomplete. Type hints have sparked a whole new ecosystem of developer tools, including libraries that use them at runtime, for instance, to validate data passing through an application. One of those libraries is Pydantic, which powers a lot of our data validation in spaCy and Think. In fact, it's a key component of spaCy's config system and helps us make sure that the config settings you pass in are valid and complete, even those provided to custom registered functions. I was first introduced to Pydantic by my colleague Sebastian and his library Fast API, which uses it extensively to define data models for API requests and responses. The idea is pretty simple. You declare a data model as a subclass of Pydantic's base model and add type hints to the fields. You can then instantiate the class with your data, and the values will be converted to the specified types if possible. If not, you will see a validation error that points out the field, its value, and the expected type. If you've worked with JSON schemas before, it's basically the same idea, just powered by type-ins. In fact, you can also export JSON schemas based on Pydantic models. Pydantic lets you use basic standard library types like int or bool, but it also includes various custom types to validate different data types. For example, types for file paths, URLs, or strict and constrained types, like a strict string that only accepts actual strings, not any types that can be coerced to a string, or a positive int, which only accepts positive integers. So, what's Pydantic used for in the config system? When you're training a model, spaCy will use the config to construct all required objects and call the registered functions with the arguments defined in their config blocks. Since the config can also express nested structures, the result of one function may also be passed into another, like a learning rate schedule that's used by the optimizer. If something is wrong and a setting is specified incorrectly or is missing, we want to be able to exit early and tell you what the problem is so you can fix it. This is done by validating the config blocks against Pydantic data models. There are two ways we can do this. First, for top-level properties in the blocks like training, we can provide a base schema. For example, the value of dropout should be a strict float, so if you pass in an integer or string, you'll see a validation error. We've also configured it to explicitly forbid extra fields, so if you typo a name, you'll see an error as well. The implementation here is pretty simple. After we've passed the config as a dictionary, we can call the schema on it and handle the validation error. Everything else is taken care of by Pydantic. In addition to just regular settings, spaCy's config also allows references to registered functions using the @ syntax. And all other settings in the block are passed into the function as arguments. Of course, we also want these functions to be able to define the types they expect. And luckily, there's already a built-in mechanism for that. Python type-ins for function parameters. To validate a config block and create the Pydantic model, we can first inspect the function arguments and their defaults and type-ins, if available. This is pretty easy using the built-in inspect module. Next, we can create a dynamic Pydantic model using this information. If a parameter doesn't specify a default value, we assume it's required. And if there's no type hint, we assume it's any. We can then call the Pydantic model on the data provided by the config block and check whether the settings are compatible function arguments. Because the config is resolved bottom-up, we already have a function's return value when we resolve and validate its parent block. For example, if we have a function that returns a list and its return value is passed into another function that expects a list, we can validate that and even catch problems where a registered function is returning an unexpected value. The dynamic Pydantic models we create for registered functions also let us provide another useful feature, autofilling. If a function defines default values, we'll know about them and we can add them back into the config if they're not present. This is important to keep the config reproducible and avoid hidden defaults. Your registered functions can still define default values, but at any point you'll be able to auto-generate a complete config with all settings that are going to be used. spaCy's init fill config command takes a partial config and outputs the validated and autofilled version of it. It can even show you a pretty visual diff so you can see which fields were added or deleted. Under the hood, a big part of machine learning is computing things with multidimensional arrays and then passing them all the way through your network and back. Even a small mistake, like a mismatch of input and output dimensions, can cost you hours or even days of painful debugging. And you only need one single hyperparameter to be set incorrectly or inconsistently for your model to produce confusing results or fall apart entirely. Debugging neural networks is probably among the most significant obstacles for developer productivity, so it's something we really wanted to tackle. If we can prevent bugs before they happen and assist developers with debugging the remaining problems, they'll be able to spend more time focusing on the interesting stuff, building the actual application. spaCy's machine learning library Think includes custom types you can use in your code, including types for the most common arrays, like floats2d for a two-dimensional array of floats, or ints1d for a one-dimensional array of integers. Even before static analysis or other fancy type checking, typing your code, especially the abstract parts, already has a big advantage. It makes it more readable. Just knowing what's supposed to go in and out can make it so much easier to understand a piece of code and share it with others. Here's an example of a layer's forward pass that returns a tuple consisting of the output array and a callback to compute the backward pass. The input array x is annotated with type floats2d, and the output y is expected to be of type floats1d. Now, if you're using a modern editor like Visual Studio Code and enable MyPy linting, the static type checker flags the returned variable y, because it detects that after the transformation, y should be a floats3d array, whereas the function expects to return a floats1d array. So, how does this work? Think implements several array transformation methods via the backend, available as model.ops. This will either be NumPy or CuPy, depending on whether you're on CPU or GPU. The reshape3f method reshapes an array of floats, so it has 3 dimensions, and its return type is defined as floats3d. This means that the static type checker knows that y in this context should have 3 dimensions, not 1, so something is likely wrong. Either the transformation, the expected input type, or the declared expected output type, or any combination of those things. You'll be able to tell this before even running the code. At runtime, a small bug like this could have easily led you down a rabbit hole of can't broadcast shape errors. You'll often be chaining layers together, so making sure the output of one layer matches the expected input of the next layer is pretty important. Model here is a so-called generic type, similar to types like list that let you specify the list item types in square brackets. Here it allows 2 additional type declarations, the input type and the output type of the layer. Again, even without static type checking, it's pretty cool to just improve readability. It makes it much more clear what a layer does, just from reading the function signature. The cool thing about MyPy is that you can extend it with custom plugins for use cases specific to your library. For Think, we implemented a plugin that performs additional checks when you use a combinator like Chain that takes 2 or more layers and composes them as a single feed-forward network. In this example, the first layer outputs a floats2d array, but the next layer expects input of type ragged, a ragged array. Even without running the code, MyPy is able to flag this mismatch that likely indicates a bug. Software projects are made of choices. That's really what any type of design is about. For Spacey 3, the questions we kept coming back to when making our decisions were all about developer productivity. This came up in lots of little decisions, and in some of the bigger architectural questions. We paid a lot of attention to details like naming, error handling, and documentation. We also thought carefully about what not to do, especially avoiding redundant shortcuts and competing abstractions. We've been especially careful to avoid API decisions that can force the user to backtrack. We want to make sure that you don't start solving a problem one way and then find you have to use an alternate API that's faster or supports some different combination of features. This is part of what we mean when we talk about providing a smooth path from prototype to production. For most projects, shipping to production is an ongoing process. It's not a one-time event. If you'll always be in development, it's not ideal to have development code that just needs to be torn down and rewritten at some point. Perhaps the most important thing we decided not to do is to hide away the complexities of machine learning. Developers need to be able to program with the library, which means putting the pieces together to build their own solutions. This is why one of our mottos is let them write code. The alternative is a library that tries to make everything just one function call. This ends up feeling like a kitchen full of unitasker gadgets. You don't want to be rummaging around a drawer of egg slicers, papaya cubers, or halibut tenderizers every day. It's much better to have a smaller set of tools you know and understand. You don't solve any problems by just abstracting away the complexities of machine learning. You need to embrace them productively. We hope you like the trade-offs we made for Spacey 3. Of course, we tried not to break too many things, and it's helped that a lot of thought went into the earlier versions of Spacey as well. So, give it a try and let us know what you built.